Hello, chemists. Let's talk some wave-particle duality in the context of the de Broglie wavelength. So the de Broglie wavelength is designed to get at the heart of this idea of wave-particle duality. Well, what does this mean? Well, when I refer to particles, again, that's my generic placeholder for really talking about small things such as subatomic particles, atoms, molecules. These particles, when these objects are really small, have both wave and particle-like characteristics. So with particle-like characteristics, what are we talking about? Well, they might have mass and therefore momentum being mass times velocity. So all particles with kinetic energy have an associated wavelength with them, which I'm using the Greek symbol lambda to represent. Now, particles that have kinetic energy are particles that would have a velocity or at least a speed if we don't know the direction. And we would say that those particles translate. So if I use the word translate or translations, I'm really referring to a particle that has kinetic energy and has an associated speed or velocity with it. What de Broglie formulated was that the wavelength of that particle that's moving is given by Planck's constant h over mass times velocity. And now this is not the wavelength of a photon. This is the expression that I have introduced earlier in the electromagnetic radiation video that I made, where the energy of a photon is equal to Planck's constant times frequency nu, which is also equal to Planck's constant times the speed of light over the wavelength of the photon, right? So this expression here does not apply to a photon. This applies to a particle that has a kinetic energy, an associated mass and velocity. So h again is Planck's constant. It has units of joules times seconds. M in this equation has units of mass in kilograms. V is velocity, in other words, units of meters per second. Notice everything here is in the SI system because a joule is a kilogram times a meter squared per second squared. So everything that in terms of units here that we're dealing with are really kilograms, meters, and seconds, which means that when you calculate lambda here, the wavelength of that particle, it would have units of meters. So all translating particles have wave-like character, and there's that word again, translating. I'm really talking about the center of mass of a particle as it translates or moves through space and has an associated momentum or kinetic energy. So all translating particles have this wave-like character. To give you an idea of how these ideas might have come about and encouraged de Broglie to develop his formula for the wavelength of a translating particle, we have a very classic experiment called the double-slit experiment. In this case, an electron beam is shot at a pair of slits that are very close together and they're very narrow. And we know something about electrons. We tend to think of these as particles, and they have mass. So when these particles hit these two slits, what you actually see on the other side are regions of high and low intensity. Matter of fact, the regions where you see color, in other words, the green bars, that's where you have constructive interference, and those white regions in between where you have very few electrons striking is destructive interference, and this is called a diffraction pattern. A diffraction pattern is a characteristic of wave behavior. And matter of fact, this is the same type of constructive destructive interference you would see in the case of mechanical waves, such as water waves. Wherever you see a green bar, that is where you have a fair amount of electrons striking. The white regions is where the electrons are not striking. And matter of fact, you can see the central bar here is the most intense, and then the intensity fades off as you move to the sides in that diffraction pattern. When I started the experiment, or at least when I started explaining the experiment, I thought of an electron as a particle having mass, and if the electron beam is moving in a certain direction, mass times velocity, it must have a momentum, it must have a kinetic energy. all characteristics of particles. Yet on the flip side here, once everything is passed through the slits, I see this diffraction pattern, which now tells me electrons have wave-like characteristics. So here I guess I put it in writing. The diffraction pattern indicates the wave-like character for a particle with mass, in this case, an electron. So what does this mean in terms of particle motion? Does this mean the electron is traveling like this in this up and down motion? Absolutely not. Okay, so don't fall into that trap of thinking a particle is moving in a wave-like pattern. So what does this wavelength actually represent? What you really should think of is that the moving particle is actually distributed through space like a wave. And matter of fact, that de Broglie wavelength would be the wavelength of that wave. And the square of the amplitude of this wave is what we call a probability density. What I'm plotting here in this graph is the amplitude of the wave on the y-axis, and then position here on the x-axis. So this would be a linear position. Let's say, if we want, we could call it the x dimension. So as a probability density, this would be the probability of finding a particle in a certain position per, because it's a density, per, in this case, if I only have one dimension, it would be per unit length. And we're going to explore this idea of probability densities later when we talk about atomic structure. But probability densities could be probability per unit area. They could also be probability per unit volume. I think what's important here to understand here is that when we're saying probability density, it's not just straight up probability. It's a probability per either length, area, or volume. So like I said, if you square the amplitude, in other words, if I square this wave, what's going to happen are these negative values down here in these regions where I got this negative amplitude, they're all going to become positive. And those regions where you have the high probability density is in these regions here. Again, if this were my x dimension, these regions here that I have the highest probability of finding the electron, because my probability density is largest in these regions. However, in these regions, because that probability density goes to 0, I would say in this particular region, maybe in this region here, my probability of finding that particle would be quite small. So if we think of the particle as moving through space like a particle, well, yeah, then as a particle moves across in this direction, for instance, well, we can think of it like an electron, like a thrown baseball, for instance. However, when we think of that particle as a wave, we actually have regions of high and low probability of finding that particle. And if this is something that you kind of have to, it is striking you as very strange, good. This is something that you really have to wrap your head around. And I'll say, in terms of science, oftentimes we think of very small particles that have these characteristics as sometimes as particles when it's easier to explain the phenomenon that we're trying to explain. Other times we might think of them as waves when that's the easier explanation for trying to explain what we're observing. So let's take an example. Let's take what do we got? An electron traveling pretty fast, 2.11 times 10 to the 6 meters per second. And let's see if we can determine the de Broglie wavelength. So here's our equation for the de Broglie wavelength. And lambda is equal to Planck's constant divided by, now the mass of an electron is 9.11 times 10 to the minus 31 kilograms. I want to make sure that I'm working in SI units here. And then this is the velocity that's given to me in meters per second, or meter second inverse. By the way, if you didn't recognize mass here times this velocity, that is a momentum. So sometimes you'll see the de Broglie wavelength written as h over p. P is a very common letter to represent momentum. If you unpack the letter p, it really means the momentum. It's really mass times velocity. And if you work through this problem, plug it into your calculator, this is the value you get. And the units are meters here because this unit of joules is a kilogram times meter squared per second squared. So everything cancels except units of length. And in terms of significant figures, this is all multiplication and division. I've got two numbers that have 3 significant figures, so my final answer is limited to the numbers with the fewest number of significant figures. And if I want, I suppose I can convert these to picometers. So if I multiply by 10 to the 12 picometers per 1 meter, I want meters in the denominator to cancel meters here. So this factor here comes from the video that I had on the metric system and metric prefixes. So meters will cancel, and I'm left with 345 picometers. By the way, typical size of an atom, that's about on the order of 100 picometers. So an electron traveling at this speed has a wavelength that's close to the size of an atom. So this would be a very, very small wavelength. Well, what about me? What if I'm late to class or whatever appointment that I have, and I have to sprint, let's say at 18 miles an hour. So what's the de Broglie wavelength if I weigh 195 pounds? All right, well, again, plug in my expression here. Plug in Planck's constant, that's in the numerator. Now my mass is in pounds, so I'm going to have to convert that to kilograms. So the conversion is 1 kilogram per this many pounds. And the way that I wrote it, I wrote pounds in the denominator, so they'll cancel. So now I got kilograms. And now I'm going to multiply by my velocity, 18 miles per hour. Now, again, this is miles per hour, so I need to convert this to meters per second. So I guess I'm going to go for time first. So there's 1 hour per 60 minutes. Put hour in the numerator, so hours cancel. And then 1 minute per 60 seconds. Put minutes in the numerator here in this conversion factor, so that minutes cancel. So now I got seconds and time, so I'm good. The only thing I have to do now is convert miles to meters. So there's my conversion from kilometers to mile, and I want miles in the denominator, so they cancel the miles here. And I've got 1,000 meters in 1 kilometer. By the way, this factor here again comes from that metric prefix video that I have. So kilometers cancel, and now I've got meters. Meters per second, so my speed looks good. And again, I've got, I guess my mass here, my weight, has 3 significant figures, so that's going to translate to only 3 significant figures in my final answer. All of these other, matter of fact, this only has 3 significant figures too, my speed, so, or my velocity, so that would also impact the number of significant figures here. All these other numbers have more significant figures, or these conversion factors are exact, so they're not going to impact that final number in terms of significant figures. Okay, well, I can convert this to picometers just like I did up above, maybe put them in the same units. And there's my wavelength in terms of picometers. Now at this point, if you compare these two numbers here, you can see my wavelength is a heck of a lot smaller, way smaller than the wavelength of that electron. And some of you might be thinking, why can we even use this expression for lambda for large objects? I mean, it seems strange enough to be using it for small objects like subatomic particles and atoms and molecules and so forth. Well, this equation is generic. And matter of fact, when applying this, you can see how small the wavelength is for me, because the main reason is because my mass is so much larger than the mass of the electron. So one thing we should always ask is, what do we learn from those calculations? At this point, maybe it's just a bunch of numbers that we've spit out of our calculator. But particles with large mass, and this was the problem with myself, or let's say with baseballs, footballs, cars, airplanes, things that have kinetic energy and are moving, they're going to have de Broglie wavelengths that are so small, their positions can be determined precisely. So again, if you think back to thinking of a particle distributed through space like a wave, with regions of high probability of finding that particle and regions of low probability of finding that particle, we don't observe that for the world around us with macroscopic objects, simply because the wavelengths are so small that their position and their probability can be precisely determined. On the other hand, when you got subatomic particles and atoms, chemically bonded atoms, those would be molecules, that translate, have kinetic energy, they're going to possess de Broglie wavelengths so that their positions are actually going to be based on probability. And again, why can't we know their positions precisely? And I had an earlier video on this. This is because of the Heisenberg uncertainty principle. You cannot know both precisely a particle's position and momentum at the same time. Now, if you think of the problems that we've been working through, I've given you, let's say, the momentum, the mass, and the velocity of a particle. When we get what that really means is that the position cannot be determined. Best we can do is find regions of high or low probability where we might or may not find that particle. So I hope you found this video useful on the de Broglie wavelength. Thanks for watching.